Hey, math people. Lecture 5 of the 6-part lecture series on analytical applications of differentiation. We're actually going to just start with a review of all the stuff I already did. So you can skip that if you want to. Remember, this video is for you, Shannon, or whatever your name is. Use pause, use the timestamps, be patient with yourself. We're going to do a review, like I said. We're going to look at the intuition behind what's called the second derivative test. We'll define it, look at it off that example, and then look at some examples. Full circle at the end. Let's math. All right, so yeah, let's just see what you can remember of all these. If you want to pause and be like, oh, that's that thing where I have to take the derivative and do the other thing, you can. But I'm just going to show the answers to this. 3, 2, 1. So yeah, at this point, if you're following along with me, you've done all of these ideas so far. I'm not going to sit and read them, because you can read. But we've done a lot of ideas with analytical applications of differentiation. It's a bit of it. We're in the slog, like the thick of it right now. So kudos for making it this far. It's a lot to juggle. Anyway, all right. So this warm up here is going to be relevant to what we do for the second derivative test. So if you want to do a little math with me right here, go ahead, use the first derivative test, which is taking that first derivative, creating that number line, figuring out the pluses and minuses. Remember, if it goes from positive slope to negative slope, that's a max. Negative slope to positive slope, that's a min. And do all that stuff with this if you'd like, because I'm going to connect to it with the second derivative test. 3, 2, 1. You should have got this, I guess. You take the first derivative, you factor it out, you get 0, negative 1, and 1. So we go from positive to negative at negative 1 and 1, and then we go vice versa at 0. This is what the graph looks like. I made it a frog because I was bored one morning. So what we want to do is we want to look at these extremas and observe the concavity at them. So rather than just talking through the context of the first derivative, we want to introduce that second derivative layer as well. So let's think about this. What's going on with the concavity here? What's going on with the concavity here? And what's going on with the concavity here? Can you maybe pick up on some pattern? Conjecture. I don't know. You tell me. 3, 2, 1. If you screamed into the abyss, I couldn't hear you. But here's the pattern. Horizontal tangents are occurring at each of these 3 points. You got that 0 slope, right? You can rest on all those points. You'll notice that when we're concaving down, I have a max. Concaving down, I have a max. When I'm concaving up, I have a min. That is no coincident. That's the point. That is the second derivative test right there. Is that when you experience a horizontal tangent via critical point stuff, if it's concaving down, we have a max. If it's concaving up, we have a min. That is called the second derivative test, which can be formally laid out right here. All right, so if f is differentiable, we say that it has a max at some point C. If the derivative is 0, and if f double prime is less than 0, we say it has a min if the derivative is 0, and f double prime is greater than 0. This is concave down, this is concave up. It behaves kind of opposite to what you would instinctively think with the inequalities. You would think, oh, max, greater. Oh, min, less. No, right? Because think about it. If you're concaving down, that is a high point. That is a maximum, the higher number. If you're concaving up, you have a low point, you have a minimum. So this is also true with just general critical points, but right now we're just kind of looking at it through the context of just the derivative. And then if the second derivative happens to be 0 or undefined, we just have to use the first derivative test instead. We're going to look at some examples. We're going to look at the one we just looked at, so we already know the answers to it, right? We know it's a max at negative 1 and 1. We know there's a min at 0. So what I want you to do, if you want to do this on your own first, is take the derivative, set it equal to 0. Listen, we already have those values. There's 0, negative 1, and 1. So just do this part. Just plug in 0, negative 1, and 1 into the second derivative. What you should see is, the ones that we labeled as maxes, your output should be less than 0. The ones we labeled as mins, your output should be greater than 0. 3, 2, 1. So yeah, that's what I did. Yeah, I got those 0, -1, and 1 again. I plugged them all into the F prime, F double prime, like concavity tester, which is, it's going to shoot out a number. I really don't care what that number is. So when I plug in 0, 32 shoots out. So it has 32 concavity up points. I don't care what that means. I don't know what that means. It just means it's super concave up. In which case, if it's concave up, it's a minimum. So, you know, for that 0, we had a relative min. And then for the other two values, we ended up getting a negative output and a negative output. Those are both concave downs. Frog, concave downs. And those were maxes. So that's the process, okay? Take the derivative, set it equal to 0, find those critical points, plug them into F double prime. If it's a positive number, concave up, min. Negative number, concave down, max. Give it a go. 3, 2, 1. I'm going to do this one. All right. First derivative set to 0. We get these 2 points. We had to do some gross factor. Sorry. All right. We plug them both into F double prime. At least it's an easy second derivative. We end up seeing that if you plug in -4/3, that is a negative number. So that would be concave down, which is a max. And if you plug in 5/2, that's a positive number for the output. And that's going to be concave up, so it's a min. And here's the language, right? So if you want to justify this on the AP exam, if you're taking that, the official justification is to observe and to mention that F prime at that critical point is 0, and F double prime is less than 0, so therefore that's a relative max. And then, you know, the opposite story for the relative min with the greater than symbol. So whatever your teacher is asking of you, right? Remember, it's every evaluator has different standards for it. But this would be like I can't imagine your teacher asking more than this level. All right, give it a go with cosine. So got to solve some trig expressions. 3, 2, 1. So yeah, I gave you, it looks like I gave you like a couple waves of cosine, but this is a slow moving cosine. That's a divide by 4, so that is moving slow. Taking that second derivative, I'm getting 0 and pi. There were more solutions. You know, there was also 2 pi, 3 pi, 4 pi, but I was multiplying everything by 4. Those would have been outside the interval, right? This is a slow, I can even show you. This is a slow moving. That's the thing, is that we don't assume that you forget these things. And then it's from negative. Wait, what? We don't assume you forget these things? Yeah, we don't assume you forget these things. There it is. But like low key, we kind of assume you forget some of these things. Yeah, okay, so it's just a slow moving cosine, which is why I'm showing you this here. And you can see we got the max, we got the min. Right, so we switch the concavity. I don't care where, but it looks like it switches at 2 pi. We have that maximum at 0. We have that minimum at 4 pi. We can see that verified by plugging that into the second derivative. When you plug in 0 here, cosine of 0 is 1, so that's a -1/6. That's less than 0. That's a downward pointing parabola at that moment. So that would be, right, downward pointing parabola at that moment. So that would be your maximum. And then if you plug in 4 pi, the 4's cancel. Cosine of pi is -1. So negative times a negative is a positive. It's concave up at that point. Concave up. And that would be your minimum. Rolling. We rolling. All right. Next one, 4th power. Give it a go. 3, 2, 1. Trap. 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 It's a trap. So yeah, if your second derivative is equal to 0, try using the first derivative test. If you tried using the second derivative test here, something weird would have happened. You would have taken the first derivative, whatever, that's fine. Set that equal to 0 to get your critical point. That's a -5. When you plug that into the second derivative, you end up getting 0 out of that, which is a problem. That is not, 0 is not greater than 0, 0 is not less than 0. So if second derivative test fails, we got to do the whole number line stuff. So what is the point of this example is that the second derivative test fails sometimes, to which we have to use the first derivative test, to which you might say, why can't I just only use the first derivative test? To which I say, Okay, so sometimes it helps to have multiple methods to arrive at the same conclusion, because there are scenarios in which one may be better than the other. So, for example, in multivariable calculus, if you have multiple inputs, you can't graph your inputs over a line. You need a plane. So the second derivative test is the only test we teach with multivariable functions, so functions with multiple inputs. Admittedly, the first derivative test kind of does everything you need for the most part within Calc 1. But this is just another way of finding extrema. All right, look at 5. Another one. Give it a go. 3, 2, 1. All right, first off, taking that first derivative, I use quotient rule simplified. I set the numerator equal to 0, and I got -1 and 1. Looks like it's going to suck plugging in these numbers into the second derivative. It sucked taking the second derivative because you had to do a really nasty quotient rule, but it's not that bad if you're good at feeling the numbers, because check this out with me. If I take this -1, I pick it up, place it into some of these x's. -1 squared is 1. 1 plus 1 is 2. So this turns into a 4. It's a positive number. That's all I really care about. Because when I plug in this negative here, a negative times a negative is a positive. So this is going to be a positive number. When I plug in -1 here, that's 1 minus 1. This is all 0. I don't care about it. And I don't even want to plug in this -1 down below because I'm raising it to a 4th power, which will always make it positive. So I have a positive number plus 0 over positive number. That is positive. So therefore, that is a minimum value. If I do the same thing with 1, even easier, this would be positive, this would be negative, this would be 0, and this would be positive. So that is a negative plus 0 over a positive. So that is a negative number. So concave down, which is a max. So yeah, I don't know. Feeling the numbers can be helpful. Does that make sense? I don't always compute when I do these like interval kind of things and plug in numbers just to test to see if it's positive or negative. I don't actually like do the full computation. I just kind of like, once I know it's going to be positive or negative, I just move on. All right, so full circle. See if you can handle this like all in one sort of review here. So find the relative minima, maxima, increase, decrease intervals, point of inflection, and intervals of concavity. So everything all at once. Give it a go. 3, 2, 1. Okay. Yeah, this one we'll get the graph at for sure. So if we're looking at, man, where do we even start, right? I would say relative extrema and increase and decrease. How we do that is we take the derivative, set it equal to 0. Who would have thought? And we use that number line again, right, with f prime. You test numbers to the left and right of those critical points. It's a polynomial, so it doesn't have any points of non-differentiability. And then we see from negative slope to positive slope at -1, that's a min. And then positive slope to negative slope at 3, that's a max. Okay, so that is, and then decreasing intervals for negative derivative, vice versa for positive. So that's the first 4, or first 3. That's parts A, B, and C. Yeah, for point of inflection, I take that second derivative, I set it equal to 0, and it's potentially at 1. I have to make sure the sign switches there, which it does. It goes from concave up to concave down at 1, so that's your point of inflection. It's concaving up, positive second derivative on the left, negative second derivative on the right, that's concave down. Notice I didn't even use second derivative test. I could have, right? I could have picked up this 3 and plugged it in over here, and that would have been a negative output, so that would have indicated a max, which, hey, look at that, it's a max. I could have plugged this -1 in over here. That would have been 1 plus 1. Wow. 2. I don't know why I had to think for that one, which is a positive number. That's concaving up, and that's your minimum. Oh, geez. Okay, that didn't happen. All right, so I'm going to just go ahead and graph this and just kind of say, hey, look at this. Isn't this awesome? So the application here is, get this, if you're stranded on an island and you don't have access to a calculator, you would know the extrema to this function. Okay, I mean, think bigger picture. If you have a problem with the application of their derivatives here, then you got a problem with me. No, that makes sense. You almost kind of should. But remember, these are conceptual building blocks. We can build into bigger, better, greater ideas off of this foundation. You know, In real life, we just look at graph, right? I'll admit that. I don't sit here and do this calculation. All right, we have a relative min at -1. We have a relative max at 3. We have that point of inflection. Where's that point of inflection? At 1? Wherever 1 is. 1 is like, that's not, it's like here-ish. It's around here. It switches concavity. And it makes sense. We're concaving up at the beginning, and then we're concaving down on that second half. So it matches. Okay, that's all. Math on.